Sure.
Igor is here. Okay, so good.
So it's a pleasure to have Eric Kilgore that will speak about Legendrian non-squeezing via microsheaves.
Yeah, so I guess I want to talk today about, as you say, Legendrian non-squeezing via microsheaves. This is sort of a horrible word. I don't ever want to say it, so I'm trying to avoid it. And instead, I'll sort of explain the idea of okay, what's going on in maybe some more friendly language in dimension 3. And then I'll talk very little bit about at the end, maybe about how to generalize. The first thing I want to do, it's about, I said the talk is about Legendrian not squeezing, so I should recall some things about sort of what contact not squeezing is, since that's sort of the jumping off point for what I want to talk about today. What's contact non squeezing? So the idea is that when we want to know if there's some kind of analog of like the Gromov non-squeezing phenomenon that exists in contact geometry. Naively, there's no such thing. If you just take like a standard contact vector space with the usual structure, okay, for me, contact manifold, there's just the structure, no form. I don't want to fix form. There's no kind of like quantitative rigidity in this space. If you take, for example, just a ball inside of here of some radius, or radius just means in Euclidean coordinates, there's a vector field, contact vector field transverse the boundary of the ball, along which you can just kind of compress it. This boundary of the contact ball is convex. So if you look for some kind of non-squeezing phenomenon in the most obvious place, you'll fail to find any. But it turns out that there is something, which was discovered by Eliashberg, Kim, and Polterovich. In the mid-2000s, which is the following. It says that, essentially says that there's some amount of symplectic rigidity persists. So if I take a ball inside of C to the n, standard symplectic vector space, R is bigger than 1. I take a little r less than, the theorem they prove says little r less than the floor of R. There's some kind of strange integrality going on. And I consider the cylinder Cn minus 1 cross disk of little r, radius little r, also means Cn. Now I look at lifts of these guys to the pre-quantization of Cn. So that's S1 cross Cn with contact structure given by the kernel of your favorite Liouville form on Cn plus some one form on S1, the non-vanishing one form on S1, which I will take to have total integral 1, just as a normalization. Then there's no contact squeezing at the pre-quantization of this ball into that of this cylinder. So what I mean by contact squeezing is there's no ambient contact, there's no contact isotopy of compactly supported of S1 cross Cn that moves this ball to be completely contained in the pre-quantization of this cylinder. Okay, so this theorem has kind of strange conditions with this floor and greater than 1. It turns out that the floor is not so important. The greater than 1 is very important, at least in high dimensions. this is still part of the same result. N greater than 1 are small. So in high dimension, we can always squeeze BR hat into, well, not even just the cylinder. Of any other radius. Somehow, if you become sufficiently small, all rigidity disappears. Once you're large enough, there's some kind of remnant of symplectic non-squeezing. Okay, so this original proof, they require some kind of integral separation. It was later improved by various people using different techniques independently. Shu and Fraser, I think, in the same year. So you can forget about the floor and just ask for inequality, the naive inequality. Still R greater than 1, big R greater than 1. So I mainly want to state this theorem just to put some context for what quantitative contact rigidity looks like, and also to sort of motivate the question I want to ask, which is whether or not there's some kind of isotropic non-squeezing in the contact setting. So in symplectic geometry, I guess I think
question. So, for example, if n is 4 and I look at ellipsoids and quantize them, is the shape of the ellipsoid that very wrong?
It's a very subtle question, but the answer is yes. But somehow here the you have to the sort of integral.
So we replace the cylinder by maybe a stretched cylinder and so on.
Yeah, so I mean, you can just do the ellipsoid into the. You can ask about the ellipsoid into ellipsoid question in this setting, and okay, this is sort of orthogonal to what I want to talk about, but there's some way to recover the integral parts of Good-Hutchings capacities. As invariants of this contact domain. But this is, I mean, okay.
Yeah, that's right.
This is something else. Okay. So this is that. So today I want to ask about this like analog of this theorem of Chekhanov from, okay, I don't actually know the year. I think it's in the early 2000s, maybe it's in the 90s still. That if I have a Lagrangian non-exact in Cn, which bounds like I don't know, minimal Maslov 2 disk area A, then L is not Hamiltonian isotopy, cannot be moved by Hamiltonian isotopy into cylinder of, open cylinder of area A. So the question is whether or not there's some analog of a statement like this in contact geometry. So the setting will I still want to ask this question about a pre-quantization, mostly because maybe somehow this is, well, okay, 2 reasons. This is the local question, and also the universal model near a Rave orbit or something. Also because there's some evidence, we at least know that contact non-squeezing holds here. There are not so many places where we actually know contact non-squeezing is a phenomenon. So question, is there a Legendrian version?
Chekhanov's result, you have Maslov 2 disk.
Probably, okay, in Chekhanov's result, maybe not. Maybe this is like Chekhanov plus Fukaya and some number of O's. Eventually you can say this, but maybe you might be right that his result is not so restricted. And the obstruction is exactly the obstruction to Lagrangian floor theory. So I somehow this in the end will be the right answer, but okay. Minimal J disk. this theorem is definitely true, and also definitely due to Chekhanov. Okay, maybe due to Chekhanov modulo. Maybe I should put adjectives in front of L, like monotone or something, but I'm not sure even this is necessary.
I think that's probably it's perfect.
So I don't know if there's a Legendrian version of this phenomenon. What I mean by that, I mean, okay, the specific example, maybe the most direct translation, direct comparisons over there. So if I take an L Lagrangian inside Cn, closed, okay, necessarily non-exact, such that the Liouville form restricted to L, I take its homology class in H1, and if it lands in the integral cohomology, then there exists Legendrian inside of this pre-quantization, which lifts L 1-to-1. So lifts means, I mean, what does it mean? There is the obvious projection, which just forgets the S1 factor. And I ask that L projects 1-to-1 onto, or projects by diffeomorphism, lambda projects by diffeomorphism onto L. And the question is whether or not, so does lambda embed, or can be lambda be Legendrian isotopied to land inside Z hat of this A, if A is the minimal disk. Okay, so this is the kind of question that I want to try to answer. So, I mean, there's actually already something known in this direction, or sort of in this direction, in dimension 3. Sort of actually, I mean, this is not really what they were interested in, but Rizal and Sullivan, Dmitrioglu, Rizal and Sullivan, we're just going to stick to D for now. They showed pretty recently, I think, I don't know, last few years, I can't remember the year exactly, after 2020, that if I have lambda in Legendrian in this pre-quantization of C, so just D2 cross, or C cross S1 with the standard form, cannot be squeezed. So they have a slightly technical definition of squeezing, which is more restrictive than what I asked for here, but than just abstract isotopy, but this is really similar, into an arbitrary D of R hat. Okay, so this is not quite so quantitative, but if you trace through their proof, they actually show that, I mean, if I take the like pre-quantization of a Lagrangian, just an embedded Lagrangian, the lift of an embedded Lagrangian bounding integral area, this thing does not squeeze into D of A. Okay, so I mean, this first line, I mean, somehow it should be telling you that this, whatever technique they're using doesn't generalize, because if it generalized, it would be somehow non-squeezing at all scales is a little bit too strong. Yep.
Can you specify the order of quantifiers in this result? So L is just an arbitrary Lagrangian circle, I guess, right?
Yeah.
And then what's the result? What does it mean cannot be squeezed into arbitrary? What does that mean?
It means, sorry, yes, you should ask for a more specific thing, indeed. It means that if I fix a lambda, then there exists in R positive, such that it cannot be Legendrian isotopy.
For some disk, you cannot squeeze.
Yes, for some disk you can't squeeze.
And then you're saying that actually you can say something it's R.
Yeah, I mean, if you fix a Legendrian, you can try to work out what the R is.
Okay.
This case, in this particular case, it's not so hard. Right. So, I mean, okay, saying something about you somehow, whatever they're doing here is sort of too strong, as we're saying, because in general, this R, I mean, I can always find some Legendrian, which sits inside a very small disk, and this is saying that there exists an even smaller disk into which you cannot squeeze. So if you could prove, you of course cannot prove a result like this in large dimension by this last line of the EKP theorem. You know, once your dimension is greater than 3, you have some limit to how small you can expect rigid sets to be. And I mean, okay, I guess even the techniques they use maybe even tell you that's not going to generalize. So the proof of this is by some kind of Thurston-Banneken type inequality near sort of localized near a Rave orbit. So if we want to try to understand some kind of Legendrian non-squeezing in general, we need some new technique in order to abstract it. Probably don't want to use the backboard. So I'm going to erase the original one. We need some new technology to, or well, somebody else a new technique. The technology is not completely new. In fact, some kind of non-squeezing phenomenon in high dimensions. Okay, I haven't said anything about why. Actually, I guess I haven't said anything about why it's hard to generalize symplectic sort of approach to contact geometry. So, okay, good. I haven't erased this theorem yet. Here, from this, you might expect that there's some reasonable generalization. Somehow the proof of this actually passes by some kind of lifting argument for symplectic cohomology to a contact invariant. Related to this fact that you can recover some remnants of good Hutchings. But it only works, this kind of lifting argument only works when you take the pre-quantization pre-image of a domain downstairs. You start with an arbitrary subset of the contact manifold, you can't relate it to anything symplectic. Legendrians are, of course, never pulled back from the base directly, since this S1 turns out to be a RAID, for the standard form. So, okay. Techniques used to prove this don't really help you for Legendrians. Similarly, the symplectic, somehow symplectic proofs of Lagrangian non-squeezing also don't really seem to help. They sort of all boil down to some kind of displacement energy argument. And if you don't fix a contact form, there's not a reasonable notion of displacement energy for Legendrians. Right? You need to take some infimum over all contact forms, and it's not so hard to show that this is just 0. Okay, at least in the pre-quantization. Somehow you can make something. There's some other work that maybe makes something work in the closed setting. Okay, so I'm going to say we need some new technique, and okay, that's just this thing. This is going to be, tool I want to use. So okay, in low dimension, give a reproof of this sort of special case of Rizal and Sullivan, using normal rulings. This is some invariant of Legendrian knots, originally introduced by Chekhanov and Pushpark. So in their case, they're in the sort of one jet of R, or and in high dimensions, we need to use microsheaves, whatever they are. Okay, so like I said at the very beginning, my main goal for the talk, I want to talk mostly about this normal rulings approach and tell you how to reprove this Rizal-Sullivan, or some part of Rizal-Sullivan in dimension 3. And then maybe at the very end, I want to sketch for you why you should believe that the proof using microsheaves is exactly the same, just with a lot more language. Okay.
There's no way to explain this in some pseudo-holomorphic curve language for some construction of.
So I can tell you the statement that corresponds to the theorem you prove here. It's like the squeezing obstruction you produce. I cannot tell you how to prove it using holomorphic curves. I don't understand. Okay, there's like maybe some hope, but I don't have a proof for you, proof that I can sort of give you in any kind of rigorous way. Okay, so maybe let's define rulings of the Legendrian. So to start, we maybe we'll live in the R-valued one jet of R, and this is just the same thing as the standard contact vector space. But I think of it as coming with sort of this front projection, which just forgets the cotangent fiber over a point. Actually, for my purposes, for the purposes of the drawings that I want to do, I want to actually remember a further projection, which just forgets everything except for the base R. So this is like the domain of a map. We're talking about an element of the jet. Okay, so under the front projection, okay, Legendrians look reasonably nice. Can always arrange that Legendrian is some mostly smooth set. The only singularities you need to allow are these cusps and crossings at a fixed moment. Always I can perturb a Legendrian knot so that its front projection looks like this. So, okay, remembering this projection, the picture will look like this. So sort of, you think of it as living over the base. Cusps always, in the jet, these sort of cusps always appear in place of vertical lines. Never allow Legendrian to be vertical. Or if you're vertical, you're not a Legendrian in the jet. Okay. So what's a ruling? A ruling is a fiberwise matching of strands of the Legendrian. So that means that over a point down here, I want to sort of somehow pair up the pre-images of L or lambda under this sort of deepest projection. So I'm going to require that this matching is continuous in some sense. What that actually means is that you should define this as a partial involution on the front of preserving fibers. And okay, let's forget about we can delete the crossings for the purpose of defining an actual involution. And then I should tell you how the crossings should behave. Okay, so we have continuous involution away from crossings. I'll ask that cusps are fixed points. So that means that as I move away from very near to a cusp, the two strands that come out of it should be paired in this ruling. Okay, now what can happen at crossings? So if I have a crossing, first thing, I never want to allow this. The two strands that come into to a transverse crossing cannot be paired. That'd be some kind of bad degeneration. So maybe I'm now in a situation like this. I have some strand up here, like this. There are two things that can happen. You could imagine this bottom strand could sort of continue to be paired with the smooth continuation of the strands it's already matched with, or it could sort of bounce off of this crossing and switch to the other one. So in this case, I want to give you a condition on when you're allowed to do this, when you're allowed to bounce off a crossing. So when which we'll call switching. So I should draw this picture a little bit differently to give you a situation that I actually allow. So this is called a switch. And I allow a crossing to switch. Only if the pairings on either side are Z mod 2 unlinked. So what does that mean? It means if I think in this fiber, my points of Legendrian are just, I don't know, since we have two things coming into a crossing, I have four strands that are relevant, and they're matched up in some way. I think of them, according to that matching, I think of them as two copies of S0, and I just ask what is their linking number in R in Z mod 2. So if they're matched like this, they're not allowed to switch because they have linking number 1. Okay, that's a ruling. It's basically some casework originally done by Chekhanov and Pushkar to check that if you fix a Legendrian, the number of normal rulings is a Legendrian isotopy invariant. Okay, so we're not exactly in this situation, so I should tell you what ruling means for. So the main observation is that the pre-quantization of C as a contact manifold is just the S1 valued one jet of R. I mean, okay, maybe you should replace C with cotangent bundle, but that's fine. Okay, so this comes also with a front projection. It's a jet, but now the front is a cylinder. But again, it's sort of, which I again want to think of as being fibered over the domain. Let's now live here. I'll draw an example, which is the one the only one that really matters. So here is the front of a lift of a Lagrangian bounding area 1. It'll just look like this. Okay, so what does ruling mean here? It turns out that there are two options, both of which are useful for us. Give them slightly different names. I'll call D ruling it's exactly the same structure as up there. Over each point in the base, you match up the strands in some way, and the crossing rules, the cusp and crossing rules are exactly the same. Is Z mod 2 unlinked in the circle. There's another choice that you could have made, where instead of just matching up the strands, we actually remember a path on S1 connecting them, and we require that that path varies continuous. There you go. Okay, homotopy class of path. That path varies continuously along the base. Okay, so it turns out that the crossing rules, when you remember a path, you should also relax them a little bit. So cusps are still the same. Oh, morally. So if I have this, the path actually matters now. And at a cusp, I require the path to contract to nothing. I don't want to leave behind an S1 or something as I crossings. So many strange things can happen now. But I mean, what really matters is that you should now interpret crossings as happening in the universal cover of this front. So I should fix a base point. I look at two lifts of the nearby. I look at the nearby lifts of strands, and I ask whether or not the crossing rule up there is satisfied in the universal cover. So the essential differences are that so two strands can be matched and cross, but they must cross like this if the path between them winds once as it goes through the crossing, at least once. The other thing that can happen is that, okay, you can have, right, your notion of linking is slightly different than it was before because it's asking about linked paths in R, which is possibly distinct from the linking of just the points in S1. Okay. There's lots of niggling technical conditions that you should write down there, but this is so essentially the same proof as Chekhanov and Pushkar show you that I can just write it up here. The counts of these two notions are invariant, are Legendrian isotope invariants. And I'll denote them by number C and number S of lambda that fix Legendrian. And now the result that powers on squeezing following. So if okay, so pi is the projection from the pre-quantization down to C. I of lambda lives inside, it sort of fits inside the disk of area 1. So maybe I actually will just say a box of area 1 because will make the picture I draw slightly easier. Then there are at least as many of these S rulings as there are C rulings. Okay. In dimension 3, the proof is very easy. The observation is just that if I have a pair of matched up strands, the distance between them measured on the circle changes by exactly the difference in slopes between the strands. The slope of the strand is bounded by sort of the cotangent the magnitude of the cotangent direction of its coordinate in the jet. So if you live down here and your slope is bounded by 1, your width is bounded by 1, the total change in angular separation between two matched strands is bounded by 1. So in particular, it can't go all the way around. That means it can't even go halfway around, right? Because it has to close back up to a cusp on the other end. Okay. What does that mean? That means that there is a canonical short path between any any matched pair of strands on the circle. Now it's not so hard. I mean, maybe if you unfold, if I give you a slightly more precise definition and you unfolded this, it's not very hard to check that if I start with a C ruling and I equip it with its canonical short path, I get an S ruling. Okay, it's another thing to check that this map is injective, but okay, maybe that's not so hard to believe because this path is, well, there's only one possible choice. Proof. Okay, so let's turn on squeezing criterion. It's fix a Legendrian, count how many C rulings it has, count how many S rulings it has. If there's more C than S, then it doesn't fit into the disk of area 1. Okay. Well, okay. So let's just look at our sole example. There's one C ruling, which does the only thing it can. It matches up the two strands that you have. There's going to be no S rulings, right? If I start at this, say at the left cusp, and I match them up, as I wind around, the only thing that can happen is the path becomes very long, right? It starts to wind all the way around the circle, and when you reach the other cusp, it wants to sort of close up to an entire copy of the S1. We don't allow that by our cusp rule, so there are just no S rulings. There's no S rulings, one C ruling, that thing's not squeezable. Okay, this tells you how to do area 1. It turns out area N is can be done by some kind of covering trick. Just pass to a large enough cover and you unwind something that winds N times. Okay. So that was pretty fast. So maybe I'll pause for questions, stall for questions, and then otherwise talk about sheaves if there aren't any.
Presumably, you could do something similar on pre-quantizations, let's say, of open surfaces or something. not necessarily the plane. I know that for surfaces, you don't get the jet. But I don't know, maybe go to some universal cover or something, or maybe the universal cover of the base, I guess.
Yeah, I mean, so indeed, defining a notion of ruling is slightly tricky in this situation. The problem is somehow that the skeleton of a surf, like the thing that serves the role of base, this R, the base R sitting downstairs, of which everything is fibered, is really like the skeleton of the, well, let's suppose you're an exact, you need to, in order to have this nice pre-quantization, this like just product pre-quantization, you need to be exact.
Yeah. So
Yeah. So if you, so the thing that plays the role of
open surface.
yeah. But so the thing that plays the role of the base R is going to be the skeleton of that Liouville manifold. And essentially there's some complication you have to deal with because the skeleton becomes some singular object instead of something smooth. So you need to understand how rulings behave over singularities. And okay, somehow once you're doing this, you're already basically in the sheaf world. Right, that somehow this might actually be easier than trying to understand the combinatorics directly.
Or you can go to the universal cover of the base, which, for whatever, open surfaces of negative Euler characteristic is just R, that do everything there. Maybe.
Maybe, I'd have to think about it. I don't know, that's a good, it's a good question. I haven't thought about it. Yeah, I mean, generalizations to manifolds that are not CN process one become complicated, as always in the quantitative world. But it's probably a very interesting question. Okay. Okay, maybe I'll try to talk briefly about high dimensions. Okay, so I mean, in the best world, everything that I just said would generalize very nicely, and I could tell you about some beautiful combinatorial invariant of high dimensional Legendrians that, like, does this matching up count. Unfortunately, I mean, basically the rules for what happens at crossings, that you need to generalize this to generic singularities of fronts in dimension greater than 3. Turns out those become extremely complicated and proliferate rapidly as the dimension gets large. So, I mean, somehow the correct replacement it's maybe better phrased in terms of some higher powered invariant. Maybe I'll tell you what that is. So, and turns out that the right invariant, in some sense, the right thing to replace a ruling by is a sheaf micro supported on. Okay. So what does this mean? So in general, I mean, okay, I say it like this. If you prefer holomorphic curves, this is like some kind of partially wrapped Fukaya category, or some object of a partially wrapped Fukaya category, where the stop is on lambda.
This is still in jet spaces.
I mean, for a moment, I will take a detour to very general Weinstein manifolds. But then I will state a result that I can prove in like the jet of T star Rn, and like, okay, if you work very hard, the strategy probably generalizes. But the conversation becomes very difficult. So if I have a Weinstein manifold, pre-quantization, Okay, it's defined exactly as before. And this thing has two sort of reasonable compactifications as contact manifolds. The first, so this thing embed, like this is some open contact manifold, and I want to embed it into some compact things. The first is the boundary. Well, I guess that's the second. The first is the boundary of the stabilization of W. So just take C cross W. This is still some Weinstein manifold. You can talk about its ideal boundary. The other is constructed exactly the same way, but some kind of critical stabilization. The boundary of T star S1 cross W. Okay. So now if I have Legendrian inside here, I mean, I can just push it forward to Legendrians over in these two spaces. Now if I have a Weinstein manifold and I have a Legendrian in the ideal boundary, there's some category associated to this, which, I mean, I'll denote by mu sheaf lambda of, well, okay, I mean, there's two. So two categories, mu sheaf lambda of C cross W, mu sheaf lambda of T star S1 cross W, which are these, okay, categories of sheaves supported on, well, let's say the Liouville cone over lambda in these manifolds. So like I said, case where lambda is nice, it's this theorem of Malchapardon and Shende that this thing is just, well, is the Rapfakaya category of C cross W stopped on lambda, likewise T star S1 stopped on. Okay, so now inside here, oops, that's gone forever. There are some distinguished subcategories which consist of the objects which are sort of simple on lambda. Maybe I don't want to describe precisely what that means, but I will say the objects that will play the role of rulings are what's called microlocal rank 1. We're supposed to generalize our rulings from above, where you match up, okay, you match up C and S as appropriate. So what's the point of that? Point here is really just that. So the sheaf category as a sheaf category itself sort of sheafifies over the skeleton. What that means is that I can look at I can do symplectic reduction along nice coisotropics and compute the sheaf category globally from sort of these local reductions plus a gluing argument. The point is that over, say W equals T star Rn, and I just look at the Liouville cone over X and Rn, and either one of these, that's either a copy of C, that's either C cross cotangent fiber or T star S1 cross cotangent fiber. And I do reduction, what I see is I just get back to either C or T star S1, and my Legendrian just sort of records its intersection with with this big coisotropic as a bunch of points on the ideal boundary. Okay, so by construction, if this thing came from the jet on the T star S1 side, my lambda maybe turns into points on the positive end by convention. We fix positive or negative. Okay, so locally, the sheaf category is the category of, I mean, okay, it's still some other sheaf category, but now on some very simple object. Correspondingly, it's like a partially octave Kaya category, either on C with some stops or on T star S1 with some stops at plus infinity. And these things are extremely combinatorial and in fact look a lot like rulings. I mean, essentially what these boil down to are, I mean, okay, there are lots of ways to express this, but I mean, maybe the right way to say it is that these are some kind of quiver representations, which are just, I mean, so maybe the right thing to say is that these are really just persistence modules with finitely many jumps. This is one way to look at them. Okay, I didn't talk about it so much, but there's a famous there's correspondence between rulings and generating functions on a particular Legendrian. And that correspondence, I mean, the point there is exactly that generating functions are just like persistence modules which jump, families of persistence modules which jump along the Legendrian and sort of mutate across crossings in a very prescribed way. It turns out that that mutation is exactly what you see in this sheaf world. And somehow, I mean, okay, maybe this is meant to justify why this strange object is like the correct notion of ruling beyond dimension 3. The second justification is that you can prove the same theorem. Okay, I'm going to be a little bit sketchy about what I mean by this, but let's say, okay, lambda living inside, what do I want to say? Yes, if lambda lives inside the pre-quantization of a cylinder of area 1, then the number of these microsheaves of local rank 1 supported on lambda in the C sense is less than or equal to the same in the S1 sense. Okay. C cross Cn, T star S1 cross Cn. Okay, by number here, I mean, take the homology category and count isomorphism classes. So, I mean, in this form, it's just like a very naive count. You don't need to do anything fancy. You can talk about the other ones, but they don't seem to be necessary. I haven't found a use for fancier ways of counting for this purpose. Okay, so this is our non-squeezing criterion in high dimensions. Maybe I should give you some applications. So maybe to say, what do I want to say? So integral twists of, okay. This is like the one-dimensional Clifford torus, if you like. Two-dimensional Clifford torus, monotone, aren't squeezable. So maybe I remind that twist tori are what you get by applying Chicano's construction to a fixed Lagrangian tor to a given monotone Lagrangian torus. Okay, you can also, I mean, the same technology basically allows you to understand integral monotone, integral non-monotone Clifford tori. Sorry, yeah, aren't squeezable. And aren't squeezable here means into the cylinder of the appropriate, of the given area. Maybe I will stop there. We're out of time. Questions?
So presumably you could define some sort of capacities based on, I don't know, fix a Legendrian. Get some, I mean, these crossings, right? Not crossings, rulings. Yeah, they have some lengths.
Mhm.
R direction, right?
Sorry.
And you could measure those. That's like, as you said, those are the finite bars in the Quranic of complex or something. So those could potentially give you some sort of measurements of domains. So all the Legendrians embeddable into a certain domain, measure all the lengths, take supreme or whatever. That would give you some sort of capacity of pre-quantized, open sets or something, and then you could.
So I think that this does not work out because this length is not defined invariant of the contact form.
But it's an integral part. I think it is well defined.
Yes.
And as we know, this is kind of the.
Yeah, that might be true.
So yeah, you won't get a capacity which is invariant by contactomorphisms, but you'll get an integer capacity, an integer valid capacity, which is.
Yeah, that's probably true. And I know that there's some work in this kind of direction. I not exactly defined this thing this way, but by Rizal and Sullivan, they've said something about this, but it wasn't. Somehow I thought there was some subtle, like at least with what they're doing, there was some subtlety with going to a pre-quantization rather than a closed contact manifold. Somehow there's some difficulty in the fact that, like, and maybe your proposal is something slightly different. So maybe this actually works out. It's an interesting thought. I haven't thought about this, so I don't have anything intelligent to say about it at the moment. But this is an interesting idea.
Can you explain what's the Symplectic holomorphic curve type invariant that all this would correspond to?
Oh yeah, sure. Okay, I'll just erase this. So I mean, the general philosophy, which depending on your religion is more or less proved, is that microlocal rank 1 objects should correspond to on lambda should correspond to augmentations of the Chekhov-Ashford DGA of this lambda. So the statement here is that I have lambda in a jet in this pre-quantization. Turns out that it's Legendrian DGA, and you can try to define Legendrian DGA directly in the pre-quantization. Turns out that it's exactly the same as the one you get in this T star S1 if you compactify to this T star S1 guy. Then I have another one. I could also embed it into this C cross W and compute its DGA there. The thing here should be given by some kind of deformation of this here, which you can make precise in the fact that this is compactifying to here is exactly installing a divisor along the open end of the pre-quantization. And now you ask, after I deform, do I see more augmentations than I do before or not? And the analog of this theorem is that if you were small, after you deform, you should not see any more augmentations than you had before. I currently don't know how to prove that sort of directly. But I don't know. I mean, it's on the list of things to think about that I haven't made it there yet.
Thank you.
More questions? If not, then thanks Eric again.